Welcome back to ece441a, 541a. Homework number 7 is due today. It doesn't have to be turned in class, but just make sure it gets turned in before the end of the day. Exam 3 is the next time we meet, which is Friday the 16th. Tomorrow, I don't know if you've RSVP'd or registered, but there is a graduate recruitment event. If you're interested, UC Davis will be here from noon until 4. I think they have a lunch from noon until 1, and then maybe sort of a one-on-one question and answer session from 1 to 4. If you're interested in graduate school, that might be something to check out. Today what I want to do is begin Bode plots. I'm assuming you've seen before, but what we want to do now is learn how to design controllers with Bode plots. How do we shape these Bode plots? And for that reason, it's nice to understand some characteristics of Bode plots. We'll discuss stability margins, gain margin and phase margin. If you've heard of that before or not, hopefully that will become more clear after today's class. And then we'll talk about really system identification. How do you find a transfer function from a Bode plot? If somebody gives you this frequency response, can you now extract from that the transfer function, the G of S? That's where I would like to go. Just as a reminder, here is what I'm thinking we should be aware of for exam number 3 in terms of the process. This is the 3rd exam, so go ahead and add another sheet of notes. You can use the front and back of those sheets, which are limited in size to the standard 8.5 by 11 inch page. Also, you can have a photocopy of table 2.3, which is the Laplace transform table. I think that was, I don't know, somebody forgot it or something last time, but I'm hoping that you don't forget that if you need it. Calculator, closed book, and closed notes otherwise. Relative to Bode plots, I'm not necessarily going to spend a lot of time on figuring out how to sketch those Bode plots. That will be up to you, and that's in Chapter 8, which is these first 4 sections are the main sections dealing with how do you sketch and learn a little bit more information about Bode plots as far as a frequency response. Chapter 10 is the design chapter. We've already been there with Root Locus. We'll go back to new sections and talk about how do we design controllers using Bode plots. If you want to just get a feel for what's going on, you can look at table 8.5 or table 9.6, and that provides you with some examples of what a transfer function looks like and what its corresponding Bode plot would look like, if you want just some reminders as to what to expect or look for when we're talking about Bode plots. Questions on where we want to go or where we're headed, or the exam 3. Hopefully the rest of the class will be here on Friday. Please remind your friends and neighbors that there is an exam on Friday. I know we haven't seen each other for a week, and sometimes that causes some problems. Let's then talk about Bode plots and try to get a better feel for what that provides us with. These Bode plots give us information about a system's frequency response. Which, if somebody gave you a Bode plot, for example, then you can tell them exactly, well, based on the approximation of reading the Bode plot, but you can now tell you how a sinusoid is going to respond if you apply it to that particular system. So, for example, it tells us how a system will respond when we hit it with the sinusoidal excitation. Pictorially, then, we have this system. It's a linear time invariant system that we've now modeled with the transfer function. We have the output and the input. And then if somebody gives you this particular Bode plot, this is now the magnitude in dB as a function of frequency, omega. The horizontal axis is usually logarithmic so that you can consolidate a lot of information in a less wide piece of paper, for example. Then you also have, corresponding to that magnitude plot, you also have the phase plot of that transfer function. And so these two can be read together. And that's probably not a very good sketch relative to what I have, but you get the idea. You now have these plots, and now what you want to be able to do is use this information to your advantage, and it might now allow you to tell something about what's going on with this system relative to stability or relative to performance. And this is the open loop frequency response of your system. And that open loop could be a combination of the plant and the controller. So those two taken together, now you're exciting that system and seeing how it behaves relative to amplitude and phase, or magnitude and phase. So here is the scenario that we're looking at. We have G of S, which again, this is the open loop transfer function, and we want to be able to tell or infer closed loop system behavior from just seeing or having access to this open loop frequency response behavior. Meaning buried inside here could be our plant and our compensator G sub C, or controller. So I'm consolidating all of those into this open loop transfer function G, and that's now producing this open loop transfer function, or this open loop Bode plot or frequency response. What we want to be able to do is talk a little bit about the system behavior or stability in general if we now have a description of the controller and plant combination relative to its frequency response. Now, the closed loop transfer function, we know from this generic configuration, is now given to us by this T, and that's our cheer. That's just this G of S over 1 plus G of S. But what we want to be able to do is use the Bode plot information, or take that, which is the open loop information, and infer closed loop system information or behavior. Information from the Bode plot can be helpful in understanding the closed loop system properties. For example, one way that we can look at that, if we look at the magnitude of g of j omega, and suppose we find, or looking at the frequency response, we notice that that magnitude is large, let's say at small frequencies. What does that imply? Well, if we now look at G relative to how it appears in the closed loop transfer function, if G is big, and big is now big relative to, let's say, 1 in the denominator, now we have big over 1 plus big. So we have big over big relative, or really, and that is going to allow us to say that at low frequencies, at small frequencies, where that magnitude of our G was big, we know in the closed loop that the transfer function now has a gain pretty close to 1, which means that any of these reference input signals in that low frequency range will pretty much track the output, or I should say the output is going to track the reference input signal. So that's the implication here. We have our closed loop transfer function has a gain near 1 at these frequencies where g of j omega is large. Which means that we have this small error between the reference signal and the output when these reference signal frequencies are in the range where the magnitude of the transfer function is large. So for reference signals at frequencies where g of j omega is large. Now, the other thing that we want to worry about, obviously, we could care less if it's large. If the whole thing is unstable, then we're not going to have satisfactory behavior. So the stability of the closed loop system is critical. So the stability of the closed loop system is governed by what? What have we always been looking at when we talk about the stability of the closed loop transfer function? We're looking at the denominator, aren't we? So we're looking at this 1 plus g of s. And now what are we have access now to the frequency response, g of j omega. And what we'll be doing then is we'll be looking at 1 plus g of j omega. If that 1 plus g of j omega is close to 0, then we know we're near this stability, instability, or this stability boundary. Meaning what we're investigating is we're saying, okay, when does this happen? When does 1 plus g of j omega equal 0? If that is true, then we will have this nearness of stability. And g of j omega now is this minus 1, which is 1 at minus 180. And that's what we use to sketch all of these root locus. But in the root locus, we were concentrating in the entire complex S-plane, and that was g of s. Now we're looking at the imaginary axis and saying, okay, if we're walking up the imaginary axis, when we are at a particular frequency, are we close to this value of 1 or a magnitude of 1 at an angle of minus 180? And we can now have these two plots. We have the magnitude plot and we have the phase plot. And we are interested in when are those sort of aligned or at such a way that g of j omega is close to simultaneously having a magnitude of 1 and a phase of minus 180. That's where we're going to end up with this instability issue or this stability issue. So we're interested in the behavior of our system's frequency response of g of j omega near a magnitude of 1 and a phase of minus 180 degrees. And that, the nearness to that sort of simultaneous satisfaction is giving rise to what we will call stability margins. So let's look at what we have. Hopefully I can sketch something that's somewhat illustrative of what's going on. Let me now just say that I have a magnitude plot that looks like this. And now let me say that my phase curve looks something like that. And I'll try to now orient those. Let's say that I now have, this is my 0 dB line for the magnitude. This is now g of j omega in dB. This is the phase of g of j omega. And suppose now that I have this dashed line representing the minus 180 degrees. Now, what I'm interested in is this condition of a magnitude of 1 and an angle of minus 180. And if those start lining up or getting close to happening at the same frequency, then I'm going to have problems. And my stability margins are trying to sort of enhance or push that from happening in terms of this alignment of frequencies. And so I'm really looking at two different frequencies. I have one frequency where my magnitude curve crosses 0 dB. And this I will call the gain crossover frequency. So let me just say omega sub g is our gain crossover. Here's omega in both plots, and those plots are aligned, meaning they're vertically consistent. And I also have this frequency of interest where my phase curve crosses minus 180 degrees, and I'll call that my phase crossover frequency. So this is my gain crossover frequency, omega sub g, and omega sub p is now my phase crossover frequency. And what I'm interested in is where those, or sort of the margin between when those would happen at the same time. Meaning, if I, for whatever reason, experienced this much additional phase delay in my system, or time delay in my system, which would then shrink my phase, this is my phase margin. If this now went down to minus 180, happening at omega sub g, then I'm right at that stability point, and I would be unstable. Meaning this distance, this might be minus 130 degrees. That means I have 50 degrees of phase margin at that particular frequency. So here is, you look at the gain crossover frequency, you now examine the distance it would take you to get to minus 180 degrees, and this is now referred to as the phase margin. You could now tolerate that much phase change before you became unstable. Likewise, if you now look at where your phase is crossing minus 180 degrees, hopefully your gain curve is below 0 dB. This is now how much you could actually increase your gain before your system went unstable. And you've already experienced how you could crank up the gain and cause instability in the root locus. The root locus showed you the pattern of poles that exist in the closed loop system, and as you cranked up the gain, if those branches were going over into the right half plane, then you could, maybe your closed loop system was stable, but now you said, oh, how much more gain can I tolerate before I go unstable? That's the gain margin. And this is how it's displayed then in the frequency response realm, or with Bode plots. And what we want to do is, if this is not behaving the way we want it to behave, or if we now have an unstable system, we want to be able to adjust these curves to actually bring back stability or enhance our stability margins. Meaning, if somebody likes your gain crossover frequency, but your phase is now below minus 180, you no longer have a stable system. You now want to introduce phase at that frequency to try to bring back stability. Now, what can we say about the gain crossover frequency omega sub g? Can we relate that to anything else that we might have in a system's behavior? If I move that gain crossover frequency to a smaller frequency, what would that tell me about my system's behavior in the closed loop? Does that tell me anything? Pardon? The air. Now the air might be, so I've talked mostly about the air. Now I guess and that's true, if you now maybe won't be able to track as accurately as many frequencies as what you could before. But if you now look at how this is related to the closed loop, this will actually influence your speed of response. That omega sub g being further to the right will give you a faster behaving system. Meaning, if let's say that we're not happy with this particular phase margin and we wanted to increase it. Well, we could just go back to this frequency and have a phase margin determined here. That means we could get that phase margin if we lowered the gain curve and had it cross 0 dB at this frequency. But that's actually going to then be trading off the speed of the response. We're slowing our system response down by dropping the gain. Those are some of the trade-offs, but that's what we want to get comfortable with, which is designing these controllers or compensators to shape these frequency response curves. So these compensators or controllers are designed to use to improve or adjust the nominal Bode plot of G of S to improve the gain margin and or the phase margin. So let's now just talk a little bit about what we have. If somebody now gave us a transfer function, what would that look like in terms of its Bode plot in just a quick sketch? Now you might have this napkin and you want to try to figure out what's going on with your particular system. So let's look at an example. Suppose now somebody gives you a G of S that looks like, so now I'm wanting to do an example. Let me label it as such. Suppose now they give you 4 over S plus 5 over S plus 0.1 and S plus 20. This, as a representation, I like to refer to that as being in the pole zero form. And that's nice to have it in that form when we're plotting poles and zeros in the S-plane. For the Bode plot, sometimes it's more convenient to actually sort of re-express this transfer function such that we normalize all of these constant coefficients to a value of 1. And then all of our action is happening in one location of each factor. We don't have to keep adjusting the gain. We've now adjusted the gain once by factoring out all of those pole and zero constant values, and now we don't have to keep adjusting the magnitude of our response. So it might be helpful to put this into time constant form, and maybe before we do that, you want to sort of see, can I follow typical sketching techniques or what I'm used to thinking about what happens with poles and zeros for a transfer function, and what we're usually used to seeing is minimum phase connections between the Bode plot and the transfer function. So if we have a minimum phase system, what does that mean by definition? Have I explained that or said that before? Have I talked about minimum phase in here? Yes or no? We talked about bicycles. Yes, no. A minimum phase system says that all of our poles and all of the zeros live in the left half plane. And when that's the case, then that gives rise to minimum phase systems, and the magnitude plot and the phase plot can be looked at in isolation and obtain the same result. If you have a non-minimum phase system, you need both plots in order to figure out what your system is. But if you're told that you have a minimum phase system, then really all you need is either the magnitude plot or the phase plot. You can get one from the other if you know where those poles and zeros live. And in a minimum phase system, they're all in the left half plane. Now, the reason for that terminology is, let's say, the following. Suppose that you now looked at, here's an S-plane, and suppose that I had a 0 here and maybe another 0 there, and I wanted to compare these two zeros. The one here, let's say this is at -1 and this is at +1. This is our minimum phase 0. So if I had to do a sketch, or if I was interested in the magnitude response of a system that looked like this, and I was just interested in this 0 factor, I could sketch the magnitude and the phase associated with that particular factor by simply evaluating or looking at what the magnitude is doing as I walk up and down this imaginary axis. Now, if I wanted to look at the magnitude, what's the magnitude, or how is the magnitude related, let's say, between LZ1 and, or let me say L sub z left and L sub z right? How do the magnitudes vary as a function of frequency between those? If I were just to look at the magnitude factor, I now have this factor. Let's say I now am looking at S plus 1, and I'm looking at S minus 1 here. If this is now j omega plus 1, this is j omega minus 1, and if I look at the magnitude of these two, how do they compare? So this is now my LZ left, and this is my LZ right. How do they compare? They're the same, aren't they? My magnitude doesn't change whether I have a right half plane 0 or a left half plane 0, but what's happening to the phase? If I look at the phase, let's just look at one frequency. Let's just say this is the phase. Let me call that theta sub z left. And now what's the phase in the right half plane? Theta sub z r. So now if I was looking at the phase of this, let's say j omega plus 1 factor, which one is smaller or minimum for the same frequency? The one in the left half plane. That's where this minimum phase description comes from, or adjective. This minimum phase system is saying for a given pole or 0 value, poles and zeros in the left half plane relative to their mirror image in the right half plane, the ones in the left half plane have a minimum phase relative to their counterparts in the right half plane. So if you now know you have a minimum phase system, that's meaning you have all of your poles and zeros in the left half plane. That's where that comes from. Or you might hear somebody call this a non-minimum phase system. So we will typically talk about or deal with minimum phase systems, but I wanted to give you that background. So if somebody starts talking about minimum phase systems, you're going, I don't know, it just means poles and zeros in the left half plane. Well, that's all you need to know maybe now for this class, but that's more of a background as to where that term comes from. And if you're going to be sketching or looking at Bode plots for non-minimum phase systems, sometimes it's beneficial to just plot their poles and zeros and start examining what's happening to the phase, because our rules for sketching fly out the window relative to the difference between minimum phase and non-minimum phase. Let's now look at this example transfer function that we had before. That's in pole zero form. Let's transform that into time constant form. Let's factor out all of the constants such that the constant term in each of those factors becomes 1. So now if I put that into time constant form, I haven't changed the transfer function at all. I've just rewritten it. Here is my g of s. I had a 4 to begin with. I'm going to factor out the 5 from upstairs. And downstairs, I think I had a pole at 0.1. And I had a pole at 20. And if I now start combining some of these, the 4 and the 5 cancel the 20, and I end up then with that 1 divided by 0.1, or a 10, and I now have 10 over s plus 5 plus 1 over s over 0.1 plus 1 and s over 20 plus 1. And if you're sketching this now on a napkin, that wasn't too hard. It was kind of set up to be nice, I guess, for this transfer function. Now we have this, that's our time constant form. What's important is where these factors change, or what we'll call break. This 0, where was the 0 located? It was located at a value of s equal to 5. That causes that factor to go to 0. So we had a 0 at minus 5. We have a pole at minus 0.1 and another pole at minus 20. We can start to see then how these are oriented or located in the frequency axis. We have a pole first at 0.1, then we have a 0 at 5, then we have another pole at minus 20. But in the frequency sense, that's happening at 0.1, 5, and 20. We also have a gain. So some of the key features, if you're just sketching this or thinking about what's happening, you might just say, well, what are my key features with this particular system? I now have a, well, one thing that you can maybe note right off the bat, which causes things to maybe be even easier, is you do not have any poles or zeros at the origin. If you do, then you will have something that's always sloping either up or down, depending on whether it's a 0 or a pole. Another thing that we can see is in the root locus, we were a lot of times interested in this asymptotic behavior, and that was governed by the pole zero excess. That's also something that we can look at here. And that tells us what's happening at high frequencies. What's our pole zero excess here? And what does that tell us now relative to the behavior of that transfer function as our frequency gets large? Now we know what the magnitude will do. Now our transfer function at high frequencies is looking like a 1 over s. And that's going to then slope consistent with a single pole. So at high frequencies, our magnitude is going to be rolling off or sloping at minus 20 dB per decade. And the phase at high frequencies will be approaching minus 90 degrees. So now we sort of know what to expect. We know that we're not going to be having any slope for low frequencies because we don't have a polar zero at the origin. We're going to be flat at low frequencies. Then we're going to start breaking up and down based on the pole and zero locations. And eventually we'll be falling off at minus 20 dB per decade in the magnitude. So it'll be flat, then it'll go down at 0.1, it'll flatten off at 5, and then it'll go down at minus 20, and that's the behavior of our magnitude plot, just by looking at some of the key features. Where's the magnitude going to start? What's our DC gain? In time constant form, that's pretty easy if you don't have poles and zeros at the origin. If you have poles and zeros at the origin, your DC gain, depending on where they're at, it could be 0 or it could be infinite, your gain. So you don't necessarily have a DC gain if you have poles at the origin. But in this case, we do not have poles and zeros at the origin. We can simply set the s's to 0, and now all of those time constant factors are gone, and all we're left with is that gain that we've isolated to begin with. We have a DC gain of 10, but we need to write that in terms of dB so that we're magnitude, in terms of our magnitude is starting at a value of 20 times the log of 10, or this is log base 10, or this is now 20 dB. And then we're going to have breaks we have a pole at omega equal to 0.1. We have a 0 at omega equal to 5, and we have a pole at omega equal to 20. So this particular break will be down in terms of it'll make our slope go negative. This one will do an adjustment up, and this one will be down again. So this is what our magnitude does. Our phase curve is a little bit more interesting because it now only goes so far in terms of phase for each factor. They start at 0 for these linear factors, and then they either go to minus 90 for poles or plus 90 for zeros. And they do that, they make that 90-degree phase change spread across 2 decades with that 2 decades spread centered at the break frequency. So our phase then, due to that pole, is going to be, well, we know where we're going to end up, and where did we start? What's our phase at DC? Zero. So now we're starting at 0, we start to go down, then we level off, and it all starts kinking and getting a little bit quick because of these, our poles and zeros are not that farly separated. So some will be turning on when some are turning off, etc. So let's now see if we can sketch what we have relative to this particular system. If we now are looking at our gain in dB, we said we were starting at 20 dB. And what else did we say? We had, in terms of frequencies, we had something at 10 to the minus 1. And let's say that we go up to 100. We're starting at 20 dB, and we're flat until we hit that first pole, and at that first pole, our slope starts to change. That first pole was at 0.1. Now we're going down at 20 dB per decade, and if nothing happened prior to going to 1, we should be at 0 dB at omega equal to 1. So this would just keep going down and down and down. Now, where is the next break that occurs? That happens at 5. Does anybody remember the log of 5? Can anybody calculate it real quick or not? I didn't plug in my... But the next thing that's happening is this log of 5. Or I'm sorry, the 0 at 5. And that's going to be between 1 and 10. And what is the log of 5? That's what I was thinking, but I never trust my memory. So this is now 70% of the way between 1 and 10. So there's 5. At 5, we're going to actually have a slope change in the positive direction. We were going down at 20 dB per decade, so that continues. But when we reach 5, then the minus 20 dB per decade gets canceled by the plus 20 dB per decade of that 0. So now we're going level until we reach our next break frequency, which is actually going to occur at 20, and is the log of 2.3 or 1.3 for 20. So now we have 30% of the distance between 10 and 100 is 20. And so now we are flat until we reach that frequency, and after that frequency, nothing more changes, and we're just going down at 20 dB per decade. So this is now our magnitude plot. And what's our phase plot look like? Well, first off, can you identify the gain crossover frequency? That one's pretty easy, isn't it, for this example? Here is our gain crossover frequency, omega sub g. Which is 1 radian per second. Now let's try to do our phase curve. We said our phase curve started, and now I need to sort of do my tick marks consistently. Here's omega. This is now 10 to the minus 2, 10 to the minus 1, 0, or 1, 10, and 100. We have 3 poles and zeros. We have a pole at 0.1, so it's going to start going down at 0.01, a decade before that, and then it will stop sloping a decade beyond that. So that's what these arrows are trying to indicate. Let's say that this is now 0 degrees. Our next factor of concern is this 0 at 5. So now we said that 5 was located 70% of the distance. We need to go back a decade before that, so now we will get something going up because it's a 0 initially, the slope, and then it will shut off at 50, which is right there. And I'm going to run out of paper. Then we have our 0 at 20. I'm sorry, our pole at 20, so it's going to kick on at 2, going down, and then it will kick off or quit sloping at 200, which is then out here in location. So what are we doing? Every time we hit one of these arrows, we need to adjust the slope. So we were flat at 0 degrees until we reach this slope. And then what's our slope change? If nothing else happened beyond that pole occurring at point 1, we would start having a phase change a decade before that, which is 0.01, and we would just change to minus 90 degrees when we reached a decade beyond 0.1, which is 1. So this guy would just go down here and level off at minus 90. Unfortunately, or fortunately, we have a 0 that kicks in a little bit before that one kicks off. And the 0 kicking in is going to flatten our slope change. But we now have, whoa, I got so caught up in this sketching. So this one would go like this. This 0 right here would go up if it was all by itself. And this pole at 20 would go down like this. And now what I have to do is put all of those pieces together, meaning I now can go down until I reach the 0. Then I'm flat, and now once this one kicks off, I'm now going up slightly, and then I go flat again. And then this one's going to kick off, and that will be my phase plot. And I don't have a phase crossover frequency, do I? Because I never reach minus 180. So this system will be stable generically, and you could see that from the root locus. But if you wanted to find the phase margin, you would see that it's bigger than 90 degrees. We'll pick up at that point after the exam. Friday is your exam, but we will start figuring out how to adjust these Bode plots by adding in controllers.